apologize in advance because this is going to be really long because we're talking about 4 different types of macromolecules and there's a lot of stuff here. However, a lot of it should be reviewed. And so rather than breaking it up into a bunch of smaller ones, I'm just doing it as one fell swoop because it's one fell swoop in your textbook as well. So first off, let's talk about what organic means. It doesn't mean anything like when Beyonce says, oh, it's a really organic experience making my new album, or, you know, somebody else says they had an organic time at Coachella. That's not what organic means at all. All organic means is it contains carbon, okay? It doesn't have anything to do with pesticides, doesn't have anything to do with how you feel or any other whatever. Contains carbon. So yeah, maybe there were some organic experiences like Coachella with some things being consumed that contain carbon, but that's beside the point. All right. When we look at organic molecules, a small molecule of which there's only, it's, you know, we've got the atoms put together and it forms this little unit, that's called a monomer. It's one of these molecules. If we put 2 of these units together, it's still pretty small, but in order to represent the fact that there are 2 of them now, we call it a dimer. So an example of a monomer would be like a glucose molecule, and you could put 2 glucose molecules together, and that would be a dimer. Okay. Now, a polymer is a chain of monomers. Okay, and the polymer can be straight chain or it can have branching, and I'll show you examples of what happens with glucose with both of them because they have specific names, and they're names that I know you already have learned in your life. And the difference between these and a macromolecule, macro is a prefix that means big. So a macromolecule has a very large number of atoms. Okay, gigantic. Okay, and we have 4 general categories of these organic molecules that are macromolecules, and this is what we're going to be talking about. So how do we get from molecules to macromolecules, and how do we get from macromolecules back to molecules? In other words, how do we take things that are polymers and make them into macromolecules and vice versa, or going in down from monomers and dimers into polymers and polymers back to dimers and monomers? There are 2 different equations. The first is called dehydration synthesis. So let's stop and just look at those words. Synthesis. That means to create something, right? So we're putting things together. And how are we doing it? By dehydrating. So what does dehydrating mean? It means you're losing water. So in dehydration synthesis, you're going to take 2 monomers, dimers, polymers, whatever, and you are going to join them together to make something that is bigger, maybe a longer polymer, maybe a macromolecule, and we are going to lose water. And the way we lose water is on each of these monomers and polymers, there's a hydrogen ion on one side and there's a hydroxyl on the other side. So in other words, it's a water molecule that has been split. Half is on this end and half is on that end of the molecule. And so when they join together, the hydrogen ion on one side is going to break off, and the hydroxyl ion on the other molecule is going to break off. The 2 are going to join together, and this will be joined to that. So you will have a longer polymer, but you also will have a waste product of water. Okay. And this is what happens in every anabolic reaction in your body. Anabolism, the building, the creating of bigger substances. Dehydration synthesis has to occur where you are losing water. Now, if you have this longer polymer and you want to break it back down, that is not going to be dehydration synthesis. It's going to be the opposite. And that's called hydrolysis or hydrolysis, with hydro meaning, so it means water, just like I did a couple videos ago, and lysis, which means to cut. So we are going to take a water molecule and cut it in 2, because a hydrogen ion and a hydroxyl ion. And so we are going to be consuming water. And so we are going to be breaking this bond in what's called a catabolic reaction and ending up with two smaller molecules, okay? This bond, when we break this bond, this releases energy. So hydrolysis releases energy. Dehydration synthesis requires energy because we need to put energy in that bond. So these are the yin and the yang to each other. And these two chemical reactions, dehydration synthesis and hydrolysis, are going to apply to the formation and the breakdown of all of our macromolecules. So when we look at these categories of the organic molecules, we're going to have four different. The first one are our carbohydrates. Second would be our lipids. You know the rest. Third would be the proteins. And students usually get stuck after here because that's all you learn about in a nutrition class. And you forget that the fourth category are the nucleic acids. So let's go through them one by one. Not in this order. I'll do it the same order as in the McKinley textbook. All right, so now it's time for a little OChem. So if you didn't love the OChem, we're not going to go deep. You're not going to have to predict anything, but yes, we're going to be talking about organic chemistry because the word organic means carbon. And all of these macromolecules contain carbon. Therefore, it's organic chemistry. All right, starting with lipids. Lipids are oils and fats. And students like me say the word fats, but fats is not correct. Oils are lipids that are liquid at room temperature, and fats are those that are solid at room temperature. They can be soft and squishy, you know, if you use butter at room temperature. But an oil will not turn to a solid in a refrigerator as a fat will. And so that includes butter, margarine, and lard. And just because I find it amusing, I found these old advertisements from the not even the 1950s, maybe the 1940s. They're young, they're in love, they eat lard, and they're holding up glasses of wine. I'm not quite sure what glasses of wine has to do with lard. I just found it amusing. And the same thing, we've got the perfect little family that's happy because they eat lard. I have no idea what the commercial industry was doing back in those days. All right, let's talk about lipids. Going back to talking about lipids, some characteristics. First off, know about lipids. They are not polar. So if you're not polar, that means you don't like water. In other words, you are hydrophobic. Okay. The other thing about lipids, these are not polymers. In other words, we don't have a monomer. Lipids are totally different. Okay. We have lots of different types of lipids, most of which we're not going to learn anything about. But I like this because it kind of gives you an idea. Like we have simple lipids, compound lipids. We've got carotenoids, which is like the stuff that gives the orange and carrots. But basically, what are lipids going to do? They're going to store energy. Triglycerides over here, these are the ones that are a storage form of energies. Phospholipids, these are the ones that are forming all the membranes of your cells. They can emulsify. The ones that are doing emulsifying are your bile acids, which are steroid related down here. We have steroid hormones, which are also the same place, and these are messengers traveling throughout your body, the estrogen and progesterone and testosterone, your body release, and it tells you to grow hair, voice to deepen, all that kind of stuff. And we also have some waxes over here, like earwax, like, you know, honeybees make honeycombs that are very protective. So the four classes of lipids we will be learning about in this course, are going to be the triglycerides, the phospholipids, the fatty acids, but not fatty acids per se, but something called icosanoids, which are derived from fatty acids, specifically when triglycerides or phospholipids go through arachidonic acid, they're going to form icosanoids. And then the fourth category are going to be steroids, because we're learning both about steroid hormones as well as bile acids. So let's go through just a little bit about each of those. So triglycerides are by far the most common form of lipids found in your body. Okay, and they give us energy support as well, energy storage, sorry, as well as support cushioning insulation. Does that sound like adipose connective tissue? Yes, because that is what is stored in adipose connective tissue. And so triglyceride, if you look at it, you can see the prefix tri, and then you see glyceride, which has to do with the molecule glycerol. So a triglyceride is a glycerol molecule to which there are 3 fatty acid chains attached. And as I said before, fatty acid chain, we can just show zigzagging because this is going to be a carbon with 2 hydrogens, a carbon with 2 hydrogens, carbon with 2 hydrogens, carbon with 2 hydrogens. But at one end, it's going to have a carbon with a hydrogen and a COOH at the end of it. And that is what makes it a fatty acid. So we're going to have 3 of these things attaching to the 3 carbons of glycerol. In other words, we're going to get rid of some hydrogens there as well. Okay. Now, there are different triglycerides, different kinds of triglycerides, depending on these little side chains. We can take this side chain and change it. We don't really care about that. This class is not a chemistry class. We're just going to talk about triglycerides in general. Okay. When we talk about fatty acids, I'm sure you've heard about saturated, unsaturated, the good fats and the bad fats. So let's talk about bad fats first. All the stuff you love, all that chocolatey stuff and buttery stuff and all those pastries, okay, they are saturated fatty acids. And what that means is when you look at this fatty acid chain, every carbon is fully saturated with hydrogen ions, the maximum number of hydrogen ions. And because of that, it makes it solid and it makes it rigid. An unsaturated fatty acid, which you will notice is here, we have lost 2 hydrogens, and so now we have a double bond between these 2 carbons. And so that puts a little kick in it and it makes it more flexible. And so this is going to give us some oils and our good fats. Well, not necessarily good fats, let's call them better fats for you. They are unsaturated fatty acids. And if it's polyunsaturated, that would mean that it has more than one set of double bonds. You can have another set here, you can have another set there, you can put double sets all over the place. And the more polyunsaturated it is, the better it is for you. So when we look at our dietary fats, we don't want our saturated fats, we don't want our trans fats. What we want are unsaturated fats. Okay. So we want to have very little trans fats, if any. We can have a little bit more saturated fats. We want to have lots of the unsaturated fats, the good fats for you. So you can stop and look at that and read these things and try to figure out how you can make your things. The unsaturated fats are really good. This is the good cholesterol. And what it does is it takes the bad cholesterol and removes it from the body. So that's why it's good for you. Okay, so that's why you want to eat olive oil, canola oil. Okay, most of your nuts. Notice it's most, it's not all. And a little bit of avocado. So you don't feel guilty about having avocado toast. All right. So continuing talking about lipids, let's talk about lipogenesis and lipolysis. So lipo has to do with lipids. Genesis, like the Bible at the beginning, Genesis, everything was created. So lipogenesis is creating lipids. And lipolysis, there's that lysis word, which means to cut. So here we are cutting a lipid down, breaking it up. So in lipogenesis, we start with the glycerol. We're going to add 1 fatty acid, then we're going to add a 2nd fatty acid, then we're going to add a 3rd fatty acid, and that's going to form a triglyceride, which technically, chemically is called triacylglycerol, but we're just going to call it triglycerides. But in case you see triacylglycerols when you're looking at chemical things in your textbook, that is the same thing as a triglycerol. So if we start with a triglycerol, we can then, through lipolysis, do 1 fatty acid off, 2 fatty acids off, 3 fatty acids off, and then we would just be left with glycerol and 3 fatty acids. So I want to make yourself some connections to stuff we've already talked about in this chemistry of life section. What is the process called that results in lipogenesis? What's the process called that results in lipolysis? Of those two processes, which one of these is going to require water? Which one of these is going to release water? Which one of these is going to require energy input? Which one of these is going to release energy? So you see, let's take this back and rethink it, because we are talking about chemical reactions, and rework this and stop this and see if you can figure out the answers to them. All right. I hope you did that. Moving on, let's talk about phospholipids. So you can see the word lipid in there, and you also can see that it's going to have a phosphate in there. So here is our phosphate. Phosphate is a phosphorus with four oxygens, and it has a -3 charge. So it is a polar molecule, and so it will attach another polar molecule to it. And that phosphate is going to attach to the glycerol. And so these three parts are forming a polar head. Now the fatty acid chains, as we all know, fat and water don't like each other. We know that every single time we try to do our dishes. And so those tails, which are fatty acid chains, are not polar. And so the way we draw a phospholipid is we put a little ball for the head, and we just draw two little legs hanging down, and you can have the zigzag if you want to like mark on the carbons, or you just do two little tails like this, and that is your phospholipid. And so the head is hydrophilic because it's polar, and the tail is hydrophobic because it is not polar. All right, and as we showed before, this is how it spontaneously would form a phospholipid bilayer to form all the membranes in your body. So all your plasma membranes have phospholipid bilayers on the outside of each cell, as well as some of your organelles have phospholipid bilayers. So think your endoplasmic reticulum, your Golgi apparatus, your vesicles, your vacuoles, those types of things. But moving on, one of the things that we have to do with fats is emulsify them. And this is going to become important when we talk about the GI system. And so if you look at your salad dressing, basically you have a bunch of oil sitting on top, and you've got vinegar sitting on the bottom. And vinegar is a water-based substance, and they don't like each other. So what do you do before you put it on your salad dressing? You sit there and you shake it, and you are emulsifying it. So what that means is you are taking one big ball of oil and you're making multiple small balls. It's the same thing you do when you put soap or detergent when doing your dishes, or when doing your laundry to get grease stains out of your laundry. It's the exact same thing. We are emulsifying the lipid. And what that means is we are going to be taking these phospholipids and putting the tails in the middle and putting the water environment on the outside. And so instead of having one big blob, we're going to have to outside, and that we can put down the sink without clogging the sink. Okay. And this is actually how we make mayonnaise, because mayonnaise is oil and water, which don't like each other, and we put an egg in there, which emulsify it, and that gives us mayonnaise. All right, so food chemistry is real chemistry. All right, so let's get back on now to our second type of lipid, and that is our steroid. And specifically, we're going to talk about these with some of our hormones. And steroids have 4 carbon rings, and if you notice of them, 3 of them have 6 carbons around them, and 1 of them has 5, and then we can have side chains attached to them. And these are components. The most common steroid in our body is going to be cholesterol, and that's because we have cholesterol in all of our plasma membranes. So make sure you watch the videos about the cell's plasma membrane. We do not need to eat cholesterol. Only found in animal products. We do not need to eat them because our liver can make cholesterol from fatty acids. And cholesterol is the precursor to all of our other steroids. From cholesterol, we can go to our cortisol steroid. We also can go to all of our sex steroids from this. So we'll learn more about that later on. Our third type, or our icosanoids, and this basically is coming from a phospholipid membrane that becomes oxidized, and so it's got like 20 carbons, okay? And so here's our phospholipid or our triglycerides, and we go through our arachidonic acid. You don't have to know that today. We will learn about it later on. And our examples of our icosanoids are prostaglandins. And prostaglandins are really important in creating our inflammatory response. Our second group are our prostacyclins. Prostacyclins are ones that at sites of injury will cause the blood vessels to dilate and will increase blood flow. The third one are thromboxanes, and these are ones that were going to cause the blood vessels to constrict and the platelets to start the clotting process. And then the fourth one, which is really important, and people didn't know about it for quite a while, and these are much later than these other ones, and these are leukotrienes, and leukotrienes are molecules that cause smooth muscle in our airways to constrict. So blocking this is a major component of asthma therapy. And so what these four molecules do, the icosanoids, is they are local signaling molecules. So they don't cause this widespread thing. They're not released over your entire body to cause an inflammatory response, absolutely everybody, but they're released locally to cause inflammatory responses. All right. We're done with lipids. Let's move on to carbohydrates. So look at that word, carbohydrates, and what does it mean? Carbo and hydro, carbo and hydro. Yes, it means a carbon and a water. Yes. So we're going to take that water molecule, we're going to break it up into a hydrogen and a hydroxyl group, the carbon in the middle. And this is a carbohydrate. And so the classic example of carbohydrate is going to be a simple sugar. And notice, simple sugar has got 6 of these molecules, which look just like it. Okay. The other hydrogen missing from here is up there, so we can bond to the next molecule. All right. So glucose, C6H12O6. Why? Because it's 6 of a carbon plus an H2O. So C6H12O6. All carbohydrates are molecules made from sugars. They're all C6H12O6 derivatives. All carbohydrates, because they are sugars, they all are going to end in the suffix "-ose", O-S-E, like glucose, fructose, galactose, maltose. Any ose that you know, ose is going to be a carbohydrate. It's going to be made of a sugar, C6H12O6. Okay, so we have simple carbohydrates. They can be one sugar molecule, like our glucose friend right here, or our galactose friend right there. Or it can be fructose, which basically, instead of being a 6-sided sugar, it's a 5-sided sugar, because it takes the 6 sugar and it pulls it off to the side. And that's what a fructose is. Okay. And so both glucose and galactose are 6-carbon sugars, and fructose is a 5-carbon sugar. And now we can put these monosaccharides, these monomers of sugars, monomer for monosaccharide for sugars, these monomers of sugars, we can put 2 of them together and form a dimer known as a disaccharide. If we put a glucose with a fructose, that forms table sugar, sucrose. If we take a glucose and add it to the other 6-carbon monosaccharide galactose, that gives us lactose, the milk sugar. If we put 2 glucoses together, that gives us maltose, as in malted milk or malt. as in some malted alcoholic beverages. As opposed to complex carbohydrates, which are polysaccharides with hundreds of thousands of sugars. And they differ whether they are just chains, whether they have branching, whether they have nitrogen. So let's look at types of polysaccharides really quick. And we're going to have 4 basic categories. The first are starch. You'll know what starch is, right? Starch is how energy, once it's no longer sugar, it's going to be stored in a plant as starch. And what it is starch followed by starch, followed by starch, followed by starch, followed by starch, followed by starch. Okay. And so we had to have some synthesis that went along here. And so we're going to have long and branched glucose molecules. And that's the difference between sugar and a starch. Now, if you compare that to cellulose, cellulose is what forms the cell walls in the plant. We as humans have the enzymes, we have the molecules that can break down starch so we can taste the sugars, but we do not have what can break down cellulose. And you're going, wait a minute, if they are both just long branches of glucose, how come we can break one down and not the other? It's because in cellulose, instead of being a sugar, a sugar, a sugar, a sugar, a sugar, every other sugar is upside down. If you look at it, it has been flipped. And because it has been flipped, it does not break the same way. And so we cannot break down cellulose. This is the dietary fiber that you flush down your toilet because you cannot absorb it. However, other animals, such as cows, can break this down. The third type of polysaccharide is glycogen. Hopefully you've heard about glycogen before. This is a storage found of energy that we find in our muscles. And more importantly, we will have a 24 to 48 hour supply in our liver. And the difference between starch and glycogen is that glycogen is branched. So this picture makes it look very simply branched, but it can be quite complex. In other words, once you have branches, you can have long chains going off in the branches. They're just not short, little 1 and 2 sugar monomers. You're going to have a long chain going on. And the fourth type of polysaccharide doesn't exist in humans, but I've been exposed to them, and that is something called chitin. And what happens here is we have a nitrogen added to each glucose marked here in green. And so it's like a long chain of starch, but with nitrogens added to it. It's the most common polysaccharide found in nature, just not in humans, because this is what forms the exoskeletons. And so, and it's also in your fungi. So we find this in mushrooms, and like if you've ever stepped on a cockroach and you get the little crunch when you're stepping on them, that is the chitin polysaccharide that you are breaking. All right. 2 other things to talk about briefly, because we're going to come back to them later on when it becomes relevant, and that is something called a glycosaminoglycan, which is a really huge carbohydrate molecule. What happens is we have all these carbs and we attach them to a nitrogen-containing group here in the middle, an amine group. Amine just means it contains nitrogen. And so if you've ever heard of the chemical heparin, which people are given when they have blood clotting, and you actually have in your body, and we'll learn about heparin a couple of times this semester, or in your joints, in your cartilage, in your bones, you have something called chondroitin sulfate, like chondro, cartilage, chondroitin sulfate. Those are both examples of these glycosaminoglycans. And when we form these glycosaminoglycans, we can then take large numbers of these, like here's one, and there's one, here's one, there one, make this huge grouping of them, and then attach it to a bigger protein. And then that's called a proteoglycan. So there's the glycan. We take the glycan, we attach it to a protein, and we call it a proteoglycan. And this is how most of them are found in the body. All right. So here's a lovely little story, because I want to break it up. I always think about every 20 minutes to break up and think about something different. So here is our breakup thing. It's Memorial Day weekend. And you go to the farmer's market and you buy it and you eat it and you go, oh my God, this is the best corn I have ever tasted. It is so sweet. And you're going, oh, I know what to do. It's sweet. I'm going to invite my significant other, and I'm going to dazzle them with this super cool, super sweet corn. And so you go back to the farmer's market and you buy half a dozen ears of them. And then school intervenes and job intervenes. So you throw them into your refrigerator. Because you're too busy. You can't even make anything. So like, you're just going to save them for the next weekend. You're going to cook them for your significant other. So you've got this hot dinner date. And you just know that this person is going to love your corn. Sweetest corn you have ever tasted. Wait, after this corn, and you've done a really good job. You didn't leave them on the counter. You threw them in the refrigerator. You let it sit there in your refrigerator for 5 to 7 days. Only now, when both of you eat this corn, you have like, yeah, this is starchy. This is like the worst corn I have ever. Okay, so I want you to stop. I don't want you to go back and think about everything we have talked about, the chemistry of life up to this point, put all the concepts together and then come tell me what you came with. Why was this horrible corn? Why was your date not impressed? What could you have done differently? All right, so let's continue back with chemistry and let's move on to our third type of organic macromolecule, and these are nucleic acids. All right, so we've got some words and I've written what they mean just to make sure everybody's on the same page, because I know you've all had this before. A nucleic acid, there are 2 types of nucleic acid, but when I ask people name a nucleic acid, I usually get that glaze or that deer in the headlights like, oh my God, you're calling on me. Think of the words that end with nucleic acid, DNA and RNA. Ribonucleic acid is RNA and deoxyribonucleic acid is DNA. Okay. So both of these have a sugar. Ribo means ribose. This is what's found in RNA. Deoxy means to lose an oxygen. So if you compare the ribose to the deoxyribose found in DNA, you notice this has 1 less oxygen. So this is the sugar, which is then going to bind to a phosphate group and form a sugar phosphate backbone. As you can see here, phosphate sugar, phosphate sugar, phosphate sugar. So this is like the side walls of a ladder. And then between the 2 side walls, we are going to have our nitrogenous bases go in between them. And when we look at our nitrogenous bases, there are 5 of them. There are adenine and guanine. Adenine and guanine have 2 rings. So they are twice as wide as the ones with the single rings, which are cytosine, thymine, and uracil. And this was a big problem when it came to figuring out how DNA was made. People played with Tinker Toys, and so they were moving like double the ones with the 2 rings and the ones with the run ring. Yeah. So we know how it looks. We form something called a nucleotide. And a nucleotide is the sugar, the phosphate, and the nitrogenous base. So this is a nucleotide right there. This is a different nucleotide. This is a different nucleotide up there. And we put them together to make nucleic acids. So when we put them together, cytosine, which is a single ring, always binds with guanine, which is a double ring, which means we're going to have 3 rings going across here. And adenine, which is a double ring, in DNA will bind with thymine, which is a single ring, giving us 3 rings again. But in RNA, there is no thymine. What there is uracil. So that will still give us 3 across. And so when we look at this sugar phosphate backbone, now we know we're going to have 3 rings of the 2 nitrogenous bases, so it is equidistant all the way across. Okay. So what are the differences between DNA and RNA? First off, one difference in nitrogen bases. They have 3 that are exactly the same, but then DNA has thymine and RNA has uracil. The second is the sugar, where DNA has deoxyribose and RNA has ribose. And the third thing is that DNA, the 2 strands attach and twist and form what's called a double helix, which we see here, whereas RNA has a single strand. Okay, it's still going to have the 3 rings hanging off the backbone once it binds to something else. But notice it's not going to be 3 rings, because some of these are going to be cytosines, some are going to be guanines, some are going to be adenines, and some are going to be uracils. So some are going to be the single rings as found in cytosine and in uracil, and some of these, and actually they color code for you. Some of them are going to be the double rings like we find in guanine and adenine. And so, yeah, I've never noticed the color coded them. So you can figure that out. All right, so let me give you a little bit of history about this. Literally, I said they played with Tinker Toys. This is Watson and Crick, are very young, 20, 30-something-year-old upstart white men here in the United States that figured out this whole DNA stuff in the 1960s, not that long ago. How did this happen? Oh, it's kind of like, young man, get a job. Summer, you don't want to be stuck here in the hot, go to Europe for the summer. So they said, okay, we're going to go to England. There was a guy in England, his name was Maurice Wilkins. He had a lab, and it was his idea to study DNA by looking at X-ray crystallography. Rosalind Franklin was his peer, treated as his underling. She had to bring him his coffee every day and all that kind of stuff. She was a PhD. She worked in his lab, and she made images. She made the images. It was Wilkins' idea to let's look at DNA by looking at X-ray crystallography, look at the crystals via X-ray. She's the one that actually did the experiments, and she's the one who said, you know what? I think it's a sugar phosphate backbone, and then we can have the 3 little rings going across, and then everything would be equidistant. All right. Who were Watson and Crick then? Well, they went to King's College and they looked at her images. She had this. They're asking her about. She goes, "Yeah, let me show you all this cool stuff, and let me tell you my theory of it." So they looked at it and they go, "Huh, yeah, I think you got it right." And so what did they do? They created a little model showing the sugar phosphate backbone and the 3 rings across. So stop this and read this little thing. So you continue. This out of the way. And that takes us to the actual article. Here is the entirety of the article about the structure of DNA. You know, this is not a 10-page essay. It's not a 20-page essay. It's not a 30-page essay. It is a 1-page essay, not even a full page in the journal Nature, because right here, this is these are our thanks to these people. Okay. This is it. April 25th, 1953. What happened as a result of this? Nobel Prizes in Physiology and Medicine. Who got the Nobel Prize? Watson and Crick. Oh, and Maurice Wilkins, because they did stuff based on Rosalind Franklin working in his lab. What about Rosalind Franklin? Did she get the Nobel Prize? No. She wasn't even nominated for a Nobel Prize because, you know, it's the 1950s. She's a female. Yeah, okay, so what's your point? So the 1962 Nobel Prize went to Watson and Crick, who stole her idea and made the model in Wilkins' lab. Okay, let's move on to proteins. So what's a protein? It is a huge macromolecule with long chains that are not branched of amino acids. So remember, lipids are made out of glycerol and fatty acids. Right. Carbohydrates are made out of sugars, and proteins are made out of amino acids. So what is an amino acid? Remember that word amino means nitrogen. So we have an amino group, a nitrogen group. We've got our carboxyl, and we've got these side chains going on again. So think about amino acids, they contain nitrogen. These side chains will tell you which amino acid it is. The side chains will also determine whether it has a charge, and if that charge is positive or negative, and also will tell you if it's polar or not polar. And based on those side chains, we have 20 different amino acids. And those same 20 amino acids are found in all living organisms. In other words, every single amino acid in your body, you have the same 20 amino acids in a cockroach. So here are the 20 amino acids. You do not have to know which ones are polar here in blue, which ones are not polar there in yellow, which ones have a positive charge there in green, and which ones have a negative charge there in purple. Just realize there are some in each of the 4 categories. All right. And so based on that, can you see how charges would have to do with attracting, forming bonds with each other, or repelling, and the same thing with polarity and charging versus non-polar? They don't really care to form bonds. You see how when we put a bunch of these amino acids together and we start clumping them together, we can start forming bonds. All right, because that has to do with forming the shape of a protein. And when we talk about the shape of the protein, we start with a sequence of amino acids, and this gives us what we call the primary shape. Just think of this as a long skein of yarn. Okay, this amino acid followed by that one, followed by this one, followed by this one, all those 20, some of the 20, 3 of the 20, 19 of the 20, whatever. Just got this long sequence of amino acids. And now it's just like a ball of yarn. Once you have the ball of yarn, you can make baby booties out of it, or you can make a scarf, or you can make socks or a hat. Has to do with what shape it gets folded into, and that has to do with polarity and charges and things like that to form bonds. So from this primary shape, we are going to form a secondary shape. And this one is going to be forming hydrogen bonds, these weak bonds, hydrogen bonds. And these hydrogen bonds are either going to form pleats, they're these beta things, or they're going to form this curvature, which is called an alpha helix thing. And so then after this secondary bond, secondary shape, we are going to form this tertiary shape. So here we have the protein, and you can see in red, we've got some of the helixes, and in blue, we've got some of the pleating. And that's because these side chains here are interacting with each other, and they are forming bonds with each other. And so this gives us the final protein shape of this one long yarn. But if you've ever knitted or crocheted, you know that sometimes you need more than one ball of yarn. And so if we take tertiary shapes and we put multiple tertiaries together, so in other words, more than one yarn, more than one sequence of amino acid, this gives us a quaternary, or the final shape. So not every protein is going to have a quaternary shape, but those that have 2 or more protein strands, those who have gone through the first 3 steps more than once, are going to interact with each other. So those are the protein shapes. So let's talk now about the protein functions. First function, we can have some structural support. So we can talk about, for instance, keratin in your hair, keratin in your skin. We can talk about the cytoskeleton in your cells giving structural support. For instance, I think these are neurons here, the axons of neurons or the dendrites of neurons, giving some structural support there. We can talk about transport, so we can have protein channels that you already know about through the plasma membranes, or we can talk about the hemoglobin transporting oxygen in the cells throughout your body. The third function would be defense. Have you ever heard of antibodies? Keep you healthy. Antibodies are a protein. So fourth, proteins, they have to do with movement. You already know about actin and myosin. So how they interact, that gives us movement of your bones by the muscles contracting. The fifth protein is, we talked earlier about how some hormones were steroid or lipid based. Majority of our hormones are not steroid based, but they're protein based. Insulin's a great example of that. And the last thing is some proteins catalyze reactions. Proteins that catalyze reactions, we call these enzymes. I will have a whole another talk about enzymes later on. But actually, let's talk about some enzymes now. Maybe it's now I talk about enzymes. I thought it was later. All right, so enzymes are long chains of amino acids. In other words, they're proteins that are folded, and we have this one area of the enzyme that's called the active site. Okay. And this active site can bind to another molecule that's called a substrate. And when it binds to it, it forms what's called the enzyme substrate complex. And this is going to cause some kind of change in shape. And oftentimes what happens is when this substrate binds to the enzyme, it will break that substrate, okay? Because the bonds and the substrate are weakened. And here we're going to end up with products. Okay? And now the enzyme is released and it can be recycled, reused. It is not destroyed in this process whatsoever. Okay? The names of enzymes end in ase. Remember, enzymes are proteins, they end in ase. And so think of something like lactose, which was a 2-sugar molecule, is going to be cut by the enzyme lactase. Maltase will cut maltose. See how this is going to work? So those suffixes are really important. OSE is a sugar, ASE is a protein enzyme that is going to be involved in a reaction. Now, proteins that are exposed to the extremes of temperature, whether too hot or too low, or the extremes of pHs, whether a high pH as in an alkaline or a low pH as base, or really strong ions, what happens there, that can break the bonds that were formed in that tertiary or quaternary structure. And that protein is said to be denatured. And so it no longer functions. It has lost its biological activity. And this actually is quite common in real life. Here's what it would look like if we took this protein and we had it interact with alcohol. You can see that this bond here between this tyrosine and asparagine is broken. So it has changed shape, so it can't do what it wants to do. But let's make it more practical. Let's talk about when you take shrimp and you put lemon or lime juice on it, or you heat them up, or you take an egg and you heat it up, or you take an egg white and you whip it, or you take milk and add salt and heat to it. All of these things are changing the protein and denaturing it by one method or another. So we eat denatured protein all the time. Doesn't mean it can't be eaten. It just means it has lost whatever biological activity it had before you denatured it. All right, so here's a little flow chart where you can pull all this chemistry together, and here's a bunch of core ideas, so feel free to stop it and read these. These are super basics. You should probably add to this. If you're feeling lost and confused about this, visit the Learning Center, whether in person or virtually, or review this stuff with your peer group, or send me questions or ask for a Zoom meeting. Believe in yourself. all got through anatomy, you all can get through physiology. Okay. So I want to thank you once again for all your hard work, and I will see you shortly with some more recordings and hopefully in person as well. Bye.